Okay. Are you there? Or have you?
No, we're here.
Fine. Yeah. By the way, I can comment one more thing about the alkaline. Oh, what is this? New share. Whiteboard. Yes. Why isn't my whiteboard showing? There it is. You see the white whiteboard. Do you see me drawing one line over the whiteboard now?
Yeah.
Yeah. So concerning the acidity of cations, I think that one of you said from soil science that this potassium and sodium was considered as alkali cations, and one can probably they don't occur on their own because they come together with some neighbors. For example, carbonates or hydrogen carbonates. This is very common ions in natural waters and in soil. And these ions, they are less acidus than these ions are basic. These are Lewis bases, also solely simply a simple model is solely from the charge. Negative charge is a clear Lewis base, and more negative charge is a stronger Lewis base. A Lewis acid, positive charge. This is a simple model for a Lewis acid. And then there are some objects that are non-charged, that are still classified as bases and acids, and they require some extra thought. But if you have potassium, for example, together with hydrogen carbonate or carbonate ions, the basic character of these anions, they will dominate over the acid character of the cation. So thus, I think one may term these potassium and sodium ions as alkali cations, because you find them in environments which is on the whole alkaline, due to the fact that they don't come alone. They come with some counterparts that are negative and strong bases. Whereas aluminum is an acid cation. There are hardly any basic ions that can compete with the acidity of aluminum. It should be hydroxide ion, but these do not usually come freely because they combine. And for example, this compound aluminum hydroxide is a very stable compound in nature, and aluminum silicates and carbonates and such things, they also form more or less stable compounds, due to the fact that they are the positive cation is a strong acid and the negative anion is a strong base. Or, well, it's not due to that fact, but we model the observation that such compounds are stable with this model, that we describe it as a strong acid and a strong base agglomeration. So let's see. Aluminum. The content of aluminum in natural waters versus pH of those waters. I mean, what one would guess is that the more aluminum, the lower the pH. And this is also the case that, from this book from a long time ago. There were two graphs from US, somewhere in US, I don't know where it is, but you can see that they have measured different lakes, and at least I can see a trend line like something like that. So the more aluminum on the y-axis here, the more acidic the water is. And it's not unique for US. Also, West Coast in Sweden has a similar tendency. But there are also, of course, other stuff that affect the pH value of a lake. Most lakes should be around 7 or above 7, actually. I don't know why they checked. So, probably I realized that if they should measure any appreciable aluminum content, they need to check acid lakes. So otherwise, all of the aluminum content would have been very, very small. Another thing that contributes to acidity, as well as a lot of other stuff, is carbon dioxide. And this is maybe nowadays mostly heard about in the circumstance with the global warming and some kind of greenhouse effects. And there seems as a global idea that one should try to decrease the disposal of carbon dioxide to the atmosphere. This is probably a wise idea, very probably. There are some people claiming that it's not occurring, that we don't have any greenhouse effect, and, or at least that as we don't have any unnatural global warming. But I think they're wrong, completely wrong, driven by some wishes that it wouldn't be like that. It's not an acute crisis, but it will be worse and worse in the future. Carbon dioxide is not very serious when it comes to acidification. In that respect, sulfur is much more serious. But as long as we burn fossil fuels, we will add sulfur unless we take care of it already in the exhaust gases from the burner. It's smaller amount than carbon dioxide, so maybe it doesn't have such a large effect globally, but at least locally where you burn the fossil fuels. Going back to carbon dioxide, that will be of main study here. There is a history. People have been looking at Antarctica and at a place called Vostok, up on the glacier here. It's very deep, something like 3 kilometers or something like that. And so one has been taking ice cores and analyze them of the content of carbon dioxide. Antarctica is a very dry place. It's cold and it snows a little bit, maybe 3 millimeters per year or something like that. So then you can actually determine if you go 1 meter down or 10 meters down or 100 meters down in the ice core. So you can have a measure of, assuming that it has been snowing similar amounts in the past per year. So then you have a measure of the age of the ice. And this is a famous figure from Vostok that in present times we see something like 290 ppms, but you know that during the last 100 years or so, this has increased to 400 or something. We should be up here somewhere now, today. High carbon dioxide they are connected to high temperature on the Earth, and low carbon dioxide researchers claim are connected to ice ages, that is low average temperature. And there are a lot of indications that the last ice age that we encountered, no one can tell anything about it. It's more than 10,000 years ago or something like that. But there are indications that there has been a lot of ice on the north and the south caps of the Earth. So that is, if one should correlate that with the Vostok ice cores, that has been connected with low carbon dioxide. And then before the ice age, it was a short period between the last ice age and the second last. There have been some repeated kind of structure. And why this repetition pattern occurs, there are some different ideas about that, but I think the major idea is now that there is a long-term variation in the solar output. That was some kind of theory given in the 1930s or something like that. But I think very many climate scientists adhere to that too. Well, this is measurements. So these are something like observations. Is there any reason to believe that high carbon dioxide should be connected to high temperatures? Yeah, in a way, I think so. This is present day. The continuation here on this scale, this is 100,000 year. Kilo year, BP, I don't know what BP stands for. But on the line here, then you see the increase in carbon dioxide measured from an island at the Hawaii island, Mauna Loa Observatory. So it's something like 390 here, but now we are at 2020, so we are somewhere here. I think it's about 400 to 414 or something like that. The content of carbon dioxide varies slightly over the Earth. So at some areas it's slightly higher, and at some areas slightly lower. But I mean, this is measured on the same place of Earth. And one can see a constant and steady increase. There is some kind of, here is some local maximum. Maybe. Perhaps they can be connected to volcanic outbreaks, but I'm not sure. Why is carbon dioxide of interest when it comes to global warming? Well, in the visible area, there comes a lot of light from the sun and heat up the surface of Earth. And Earth is approximately, what is it, 273 Kelvin is something like 0 Celsius, yes. It is around 0 Celsius, or maybe slightly higher, 15 Celsius plus or something. So that corresponds to a body that has that temperature corresponds to something called a black body that radiates only depending on that it has some certain temperature. This is in the infrared range, around 10, 15 micrometers. What does it has to do with carbon dioxide? Well, carbon dioxide actually, both carbon dioxide and water absorbs in those areas. So if you here is a picture with the Earth's surface. Sorry. If you have an absorption of an IR quanta of a light from the Earth on some molecule, then it is excited, and then when it is relaxed, then it will re-radiate that radiation, and there is no reason why it should re-radiate in any certain direction. So some of the directions will be re-radiated below. So having these two gases in the atmosphere will sort of cover up. It's like a window in a greenhouse that saves the heat on Earth. Depending on the distance from the sun, I think the Earth should be projected to have -15 as average temperature. But because of the greenhouse gases, then we have +15 degrees instead. And the major greenhouse gas is water. So carbon dioxide is more or less unimportant in this respect. At least it has perhaps 1 or 2% effect due to the amount of water in the atmosphere. On the other hand, we as humans, we can't affect the water content in the atmosphere, but we could avoid increasing the amount of carbon dioxide. And this is what it deals with all of these discussions about the greenhouse effect. It's a slight increase, but this slight increase may have serious effects, and this is what one is afraid of. I think it's a real threat. Carbon dioxide, when it goes out in the atmosphere, for example, by fossil fuel combustion or cement production, for example. I'm sure you heard about the problem with the Cementas, a Swedish company, cement and concrete production company on Gotland. When they manufacture this cement, a lot of carbon dioxide is released to the atmosphere. So a way to decrease the amount of carbon dioxide would be to avoid cement production, but this is very, very central to modern society. We build houses of concrete. If one should only build houses out of wood, that would be less of a problem, but it's not easy to go back to wooden house maybe, but in some respect, several companies are planning to do a lot more wooden constructions. Wood is light and well, sustainable in some sense, at least, unless you burn it. But there is in this figure 7.7 billions of tons of carbon dioxide added to atmosphere every year. Forests, they both give off and take in carbon dioxide. So according to this figure, the forests, they do consume carbon dioxide total. And also carbon dioxide dissolves in the water in oceans. And you see, compared to the 7.7 plus 1, that's 8.8. So there is more added than deposited. So perhaps these total amount of 800 billion tons of carbon dioxide in the atmosphere, it increases slowly with saying something like 4 billion tons every year. A possibility would be to increase the speed of absorption in the oceans, or to decrease the addition. Then perhaps one could find some kind of steady state here, or decrease maybe. Problem connected to this carbon dioxide addition to the atmosphere is the fact that a small increase in temperature does not necessarily mean a large problem for humans, but small increase in temperature also increases the evaporation of water. Thus, the amount of gaseous water in the atmosphere increases. We will have more severe rain and storms, hurricanes, etc. Meteorologists, they say that the amount of energy in the atmosphere increases. But when we evaporate water, we increase the energy state of each water molecule. So that is a way to, one can say that addition of water vapor to the atmosphere is equivalent to increasing the energy content of the atmosphere, meaning that it will rain more heavily and we will have more severe storms in future. This is perhaps not nice, at least when the storms goes to that level that houses blow down and a lot of other stuff.
Did you say that the carbon dioxide had an effect on this evaporation, or?
Yes, the extra added carbon dioxide means a small increase in temperature, because it will
yeah, of
add
course,
to this
evaporation.
but I mean 1 degree warmer climate is of no concern here in Sweden, one could think, but actually I think it is, because 1 degree warmer climate means a lot more water in the atmosphere, and water is connected to rain and storms and such things, and they are side effects. It's not the direct effect of the carbon dioxide, but what the carbon dioxide give rise to via this small temperature increase that is serious. I think so, at least.
Yeah, thank you.
Yeah. So how should you get rid of the carbon dioxide? You can, this is a strange word, sequestration. You can lock it in or bind it to some kind of molecules, but this is very expensive, and it's such a large amount. What was it? It was 4 billion tons. We could absorb it in sodium hydroxide and then place an order for 4 billion tons of sodium hydroxide to some manufacturer, and they wouldn't believe their eyes. It's more than the annual production in the whole world, I think. But when this carbon dioxide is produced, you could, for example, from the exhaust gases, they can contain a lot of carbon dioxide. So then it may be easier to separate the carbon dioxide and freeze it, for example, just physical condensation. And then in the old times, we used to throw things in the sea, and then we got rid of it, and no one was worried anymore. This is slightly not criticize the idea nowadays, hopefully. But still, we have been looking at similar things at least. It must be much easier to separate carbon dioxide from the exhaust gases than from air, because the content in air is so small. The partial pressure is 400 ppm or something like that. So you need to process a lot of air, and with a very effective process. And they are on their way of actually finding, well, really working processes. But I'm not sure. There are some processes actually separating carbon dioxide, but that is mostly at the places where it's produced in large amount. For example, at cement factories and fossil fuel power plants and such. You could have chemical basic environment, sodium hydroxide, let's say, and then you can absorb this one. If you can do this in a cyclic way to absorb and then regenerate at the expense of some energy, there will be a larger need of electricity in the future, at least if one should introduce a lot of extra processes. And then one can store it, for example, in the ground or at lakes at the bottom of the sea. Because carbon dioxide, here's a phase diagram, a function of temperature and pressure. So temperature will stay around something like 0 degrees and slightly above. It's a gas up to 10 atmospheres or something like that, but then it becomes a liquid. 100 atmospheres, this is 1,000 meters down in the sea. And 10,000 meters, it's 1,000 atmospheres pressure. So you could actually, in principle, if you produce carbon dioxide and catch it up in some sense, you can via some pipeline, you can put it in at the bottom of the sea. It should be quite deep, more than say 4,000 meters according to this figure. And as long as the sea and the bottom of the sea is stable, this is not a bad idea. But the first earthquake we come and this that stirs the sea, then we could actually suffer from a large increase in the carbon dioxide. So I think one should avoid collecting a lot of carbon dioxide at the bottom of the sea. This is also, I think, what hardly anyone deposits carbon dioxide in the sea nowadays. What is done is that you pump down carbon dioxide in the ground in old gas reserves, oil or gas reserves. They have been tight. The ground around has been tight towards leakage of natural gas, then it should probably be tight towards leakage of carbon dioxide also. And then one expect to have carbon dioxide reacting with, for example, limestone. This is a long-term process. It will take, it's approximately as depositing the nuclear waste in the ground that Sweden does or should do. We are still collecting it above on surface, I think, or in some low deposit. But it's a matter of 100,000 years or something like that. So perhaps it's a very, very long-term period before the carbon dioxide has been reacting with the ground and with the basic minerals that occurs in the ground. It's easy to say, but less easy to do. Maybe better to avoid producing so much carbon dioxide. But we'll see what happens in the future. Or if we just arrange with more forests, they will take care of the carbon dioxide and convert it to wood, perhaps. But neither that will be easy to accomplish. I think the situation for the moment is that the amount of forests decrease, perhaps, on by various reasons. So, storage of carbon dioxide. I mean, soil and wood is perhaps they estimate here 100 billion tons per year. Leaf litter, yeah, production of litter. This is perhaps small amounts, but you could probably store a lot of carbon dioxide in oceans, or if one would precipitate it as carbonates or something like that. But there is no way to actually precipitate all carbon dioxide because there is simply not enough cations available. Storing it in a neutral ocean will acidify the ocean slightly, and an acidified ocean has much less capacity of storing carbon dioxide. We will see that this is equivalent to carbonating water. This is easy if you have tap water that is pH 8 or something like that. But if you acidify the water, it will not accept a lot of carbon dioxide. And or already carbonated water is slightly acidic. Could be down to pH 4.5 or something, even 4. Now let's see. Coming to some equilibria. Clock is 10:40. Sorry, I just need to. How comfortable are you with this? Is some formulas from the compendium KZ 4007 available on Athena. It's chapter 5, or is it 6? Better look. Yeah, it's either 5 or 6 at least in this compendium that deals with carbon dioxide and the carbonate system, we say. What about carbonate system? Let's see. Get the whiteboard. Carbon dioxide we have been speaking about. From a chemical point of view, when it reacts with water, one can claim it should be converted to carbonic acid, water solution of carbonic acid. So here we have two different types of carbon dioxide. What happened now? It's missed from my pen. Do you see this?
Yeah.
All formulas now. Okay, then we'll see if I can whiteboard. So, hey, this is not easy. So carbon, sorry, I can't use the annotation in this mode. Carbon dioxide, if it is in gaseous, here I written it as carbon dioxide aqueous.
And we can only see the whiteboard. I think you're showing something else.
Wow. Whiteboard. So now you see the whiteboard.
Yeah.
Yeah, fine. And this carbon dioxide, one could also speak about it as plus water going to carbon dioxide aqueous, or if we want to include that, we could sort of say gaseous or aqueous, or select one of them if you need. So that is different ways to look upon carbon dioxide associated with water. Is it in pure gas form? Is it dissolved? Or has it reacted with water in order to form carbonic acid? Or did this carbonic acid did it dissociate into hydrogen ions and hydrogen carbonate ions? The hydrogen carbonate ions I see as a sort of carbon dioxide, but both first it has been undergoing the reaction with water to form carbonic acid, and the carbonic acid has been dissociated, but the carbon, at least in the hydrogen carbonate, comes from carbon dioxide, and this hydrogen carbonate ion, it will also possibly dissociate into another hydrogen ions, and the final item, the least hydrogen containing carbon dioxide species, is the carbonate ion. Now, all of these reactions can be described as equilibria, that is with a right arrow and a left arrow simultaneously. Equilibria in chemistry, they are never static, but more or less always dynamic. Something happens more or less all the time. But on average, since the atoms and molecules are so small, the total content, the concentrations, or actually the what we call activities of the different species, they will be, reach some steady state. And that is what we then use for defining these equilibria. Now let's see. Clear drawings. Close this one and that one. Then we return back to this one. Now you see this whole bunch of formulas, I hope.
We do.
Yeah. So a couple of equilibria carbon dioxide form carbonic acid, or that one disintegrating. There are two carbonic acids here, one with a star as a superscript. This means both real carbonic acid and also just dissolved carbon dioxide, because in the dissolved carbon dioxide, that is a way to produce the real acid. But this is perhaps mostly academic. We can stay with the idea that carbon dioxide is an acid, and we don't care about if it's a real molecule with that formula or if it's a hydrated carbon dioxide molecule. We still treat them as carbonic acid. The production, when one of the products from decomposition of carbonic acid is hydrogen carbonate ion. And this one can undergo further decomposition. Here are some messy formulas that illustrates the equilibrium constants. This is the equilibrium constants for the formation of carbonic acid, and the Ka is the first acidity constant, and Ka2 is the second acidity constant for the carbonic acid system. And here are some values for the equilibrium constants. Perhaps one should it should be enough with we stay with this star version. So if the Ka is 4 times 10 to the minus 7, or if the pKa is 6.35, we note that carbonic acid is quite a weak acid, and the hydrogen carbonate is still weaker. The acidity constant is 10 to the minus 11, or the pK is 10.33 or something like that, which is a very, very weak acid. This could actually be termed a base, which it sometimes is considered as. It's a stronger base than an acid, but it can be both, which is in a way good. Now let's see. Time is running, sorry. 10:50, we need a break, I think. Say 5 minutes past 11. Is that okay?
Okay.